This section is still about work, and we're talking about work done by conservative forces. In this little section, we're going to look at constant force and work. So if I have a constant force, you'll notice the force is constant all the way across here. The work is equal to force times the change in distance, or the displacement. It can be used to calculate the work done by the force if it's moved from point A over to point B. Basically, all we have to do here is find the area underneath the curve, underneath our flat line. Once we know that area, that would then be force times distance, and that should be equal to the work that is done. If I have a variable force, it makes it a little bit more difficult because I've got a curve. It's a lot harder to try to find out what the area is under this curve. In order to do this algebraically, it's pretty easy to do if you just do geometry. We can't just multiply the force times the distance. We actually have to split this one into a couple different things. We need to split it up into a rectangle first, then we need to split it up into a triangle. Once we know both of those, so once we know the area of both, we can add them together. But we're going to have a little bit of an error because there's a slight curve there. If we use calculus, we can use something called integration, and that can help us find out what that variable force then gives us in terms of work. Springs are something that can give us kind of a variable force, and anytime you have a spring, if you compress it or you stretch it from equilibrium, that spring does negative work since the spring pulls in the opposite direction of the motion. So our angle there is 180, and cosine of 180 would be a negative number. The work done by a spring is best illustrated with the equation Ws is equal to negative 1/2 k times x squared, where Ws is the work done by the spring in joules, k is the force constant of the spring that we can figure out using our force equations, and x is the displacement from equilibrium. The force that is done, that does the stretching, does positive work, so it's in the opposite direction. So if you stretch a spring or if you compress a spring, that is going to be positive, and it's equal to the magnitude of the work done by the spring. So here's an equation that illustrates that. It says that the applied force, so the force that you put on the spring, is equal to the opposite of the spring work, and that's equal to positive 1/2 kx squared. In the next section here, we'll actually look at kind of an example to show you what happens. So for this one, in our little graph, we see that we have a mass right here, and what we're going to do to that mass is we're going to stretch it. When we stretch it, the x here goes in one direction to the right. The force of the spring is in the opposite direction, and by Hooke's law we know that the force of the spring is equal to negative kx. Whether you're stretching it or compressing it doesn't matter, it's always going to be negative. So here's the force, the variable force of the spring, and in order to find out how much work that spring does, we need to look at the area. That's negative 1/2 kx squared, and so that would be the negative shaded area here, or the area of the triangle itself. We're going to do this problem in the next section.